Okay. This is just to show you that there's always a relevant XKCD. I couldn't not show you this because it was the one from like yesterday. I put it up before class started so that you had time to laugh. Ha 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 ha. It's not very funny, but it's relevant. Anyway. Okay, so where were we? So we've been talking about connectionist networks as an alternative to the whole good old-fashioned AI thing that we were trying before, and as an alternative in a deep way, because we're rejecting this fundamental assumption of the traditional approach to AI, which was that the mind is fundamentally language-like. The kind of exciting part of this research program, the part that actually distinguishes it from the one that came before it, was the belief that the mind is not structured at its root like a language. Whereas the Go-Fi people thought that was their basic assumption. Look, we're going to build minds, we're going to build them out of language manipulating, logic rule following structures. And the connectionists say, no, actually, that's not what we're going to do. What we're going to do is build things that are just that just have patterns of activity. So like I showed you the kind of the basic parts of the neuron that are captured by the connectionist networks. Notice that there's nothing really like a we were just before class we were talking about neurotransmitters. There's nothing like serotonin or dopamine floating in between these neurons. There's just patterns of activity. But the thing to notice, the thing to keep in mind that distinguishes connectionist networks from Go-Fi machines is that they're made of patterns of activity. And those patterns of activity are not language-like. You build these on computers, typically, right? So in some sense, they're made up of ones and zeros. But in a deep way, you could build them out of just about anything. So you could have buckets of water pouring from one to the other. Yeah?
I don't see the slides.
Oh, I tried to just post them minutes ago. Are they not there? 1 second. Haha, I got halfway through posting them and then didn't. Thank you for that. They should, they're up now. Well, that was fast. That's nice to know that it happens fast. You're welcome. Thank you for pointing that out. I don't want you to be slideless. Okay, so these patterns of activity are not structured like a language. They could be literally like electrical pulses. They could be a number of ants walking down tubes. They could be buckets of water being poured from one container to another. These could be represented, these could be instantiated in any number of things. The fact that we do instantiate them on computers is a fact about what's convenient to us, but not really a fact about how the system is fundamentally structured. And that's what we're asking. So what's the fundamental structure in which we're realizing these models and hopefully modeling the mind? So what's the fundamental structure of the mind? So this is supposed to be a radical alternative, an alternative that rejects the basic assumption of the whole research project that we've been talking about for a couple of weeks now. We saw that this started out fairly simply with perceptrons. We talked a little bit about the limits of these things. They are linear classifiers. They are only capable of distinguishing things that are linearly separable. So they can't do things like exclusive OR. They can't do fancy stuff. But this was just a sort of limit of the very early, the 1950s version of neural networks. Once we got to the 1980s versions of neural networks, we found that these could do nonlinear classification tasks. They could do exclusive OR. They could do much fancier stuff. And they can do things like messy categorization tasks. So one of the things that good old-fashioned AI programs really struggled with was doing categorization tasks where the data is messy, where the boundaries are unclear, where the kind of like there aren't crisp categories. Like good old-fashioned AI in some deep way was instantiating the classical notion of concepts, wasn't it? So if you remember the Psych project where they tried to program in essentially necessary and sufficient conditions for concepts, that's the kind of a basic assumption of the good old-fashioned AI project. That's not necessary, but it seemed to be the way things went. And these architectures, the neural net architectures, are much, much better at dealing with messy data, data that's not very clean, data that's not very clear in doing the kind of tasks that we do all the time. So currently you're listening to my voice, or some of your mind is listening to my voice, and you're interpreting my words despite the fact that there's all kinds of noise. There's echoes in the room, there's other sounds, you've got some like if you've got tinnitus, you're internally generating some noise. So like lots and lots of noise in the data stream that you got all the time, but you're nonetheless most of the time able to deal with it. So these neural networks seem to be able to do stuff that we can do that good old-fashioned AI systems couldn't do. So that's kind of an exciting advance, right? These things have basically different architecture, and they're able to do stuff that good old-fashioned AI stuff just couldn't do. We talked a little bit about how they're trained, and that's kind of where we ended off last time. Again, in the 80s and the early 90s, this is basically the method that they used, the backpropagation of error, which was the following. You set the weights randomly, just sort of set them to whatever, and then feed it some data, and then see what it spits out. And so if it's, these output layers give you probability, so how likely is that an A, a B, a C, or a D? And if you know what the answer was, you can tell it how wrong it was. So given some output, you quantify the incorrectness of the output, and then try to assign blame, say, who did that? Who messed this up, right? You try to figure out what's the smallest change you can make to the weighting of these neurons, between the neurons, and then make the smallest change that generates the biggest reduction in the error. And you just do that iteratively. Yeah?
Is the smallest condition just to prevent hard coding?
I think the smallest condition is to prevent it from jumping around randomly. So you want it to be iteratively closing in on the optimal solution rather than jumping around, which would kind of lead you to the possibility of never, so the hope is that this thing is going to converge on the answer or the optimal sort of like way of dealing with the information. So to promote convergence, I think that's why you have it make the smallest change. And then we talked about some of the limits of that. It was the same limits as the hill climbing heuristic, which is that you can get stuck in a local optima. So you can get stuck in something where any small change makes it worse, but if you were willing to make a big change, you could get out of that and get an even better solution. So that was one of the worries about hill climbing. And then we talked a little bit about one of the strategies for dealing with the problems with hill climbing, which was plasticity, this idea that you can not only change the weights, but change the actual way in which the nodes, the neurons, are connected with each other. And this is one decent strategy for making those bigger jumps that leads to getting out of your local optima. Yeah? And that's where we got last time. Is that stuff all okay? Questions or concerns? Okay. So let's move on to talk about unsupervised learning. So briefly, let's just talk about this distinction between supervised and unsupervised learning. So last time I was talking bad a little bit about supervised learning, especially if these things are supposed to be models of the mind, right? Because I made the case to you that lots of your learning is substantially unsupervised. So it's not the case that for every time you try to learn a thing, you know what the answer should have been ahead of time. And that's clearly how these backpropagation of error algorithms work, right? Somebody knows the correct answer. Somebody's feeding it the correct answers over and over and over again. And what it does is just learn to model your understanding of the correct answer. So there's kind of intelligence being fed into the training process of the system. And what would be nice to have is a system that learns by itself, kind of like you do, to some degree. So I would like, as we're talking about, so today we're going to talk about unsupervised learning or semi-supervised learning. And I'd like you to be thinking about a few questions as we go along. So here are some questions to be thinking about. And they're questions that are in some sense meant to dampen our hopes for this stuff as an account of strong AI. That is to say, even with so-called unsupervised learning, they're still giving the system goals, Or where, here's a question, where do the goals for the system come from? And is that a worry thinking about this as a potentially strong AI project? So one question you could ask yourself is, where do the goals of the system come from? What are its goals and where do they come from? And then where do your goals come from? How did you acquire your goals? So when you're trying to learn something, you presumably have a goal state in mind. Or when anytime you're trying to transform yourself throughout your development as a human, you've got some goal state that you're trying to get towards. Otherwise, you're just changing at random. And presumably, because we've talked about the space of, like the size of spaces of possibilities, just changing at random isn't really a good strategy for most situations that you're in. You're trying to change yourself in some pre-specified way or some specified way. Where do those goals come from? Few options. You could generate them yourself. You could take them from society. Maybe somebody's explicitly given you a goal state. Or they could be programmed in by evolution or God. As far as I can tell, those are the kind of range of options for where your goals, either you did them, your society did them, or you were hardwired with them in some deeper way. So to some extent, we might be doing supervised learning as well, especially in the third case where you got a goal hardwired. So you've probably got a goal of like not being in horrible physical pain all the time. That sounds like a pretty good goal to me. And I suspect that one might be hardwired from evolution, right? So evolution wants you to organize yourself, so you try to walk in a certain way, and that way is to like minimize joint damage, because at least one of the constraints on how you move through the world, right? You try not to bump into things, you try not to fall off high cliffs and stuff, right? Those are all goals that seem to be in some sense built in, and you could use them as a kind of form of supervised learning. So as a baby, when you're trying to understand how to move through the world, if you really hurt yourself, you say, that's an error signal. And I'm gonna that was a signal that I did something wrong, and I'm gonna try to modify my behavior going forward to not have that happen again, right? If you touch this hot stove, you get a very strong error signal, and you will remember very quickly, you'll be like, that was a big error signal for me, and I'm gonna try to not do that again. Very few people fail to learn that lesson after a few tries, right? Very few people don't have that as a goal to like not get badly burned, yeah? So that seems like one sense in which we can think about even the supervised learning as something that may be analogous to what we're doing. But of course, evolution can't give you all of your goals. Evolution can only give you goals that have been very, very stable in your environment for a very long time, right? It can only program in goals that you would have encountered for the last 1,000 years, 10,000 years, 100,000 years. Evolution works over typically very long time scales, or at least genetic evolution does. So probably it's not the case that we can just say, well, all of your goals are given by evolution. So you need to be doing at least some, and probably it's not even going to be the case that you can say all of your goals are given to you by society, because human level intelligence involves sometimes not listening to society. I hope that you've had at least some of that experience in your life where you're like, society tells me I should be like this, but I would like to be like that, right? We at least should agree that that's a thing that humans are capable of, and so that if we are going to understand human level intelligence, we should understand that aspect. So that's a kind of endogenously generated goal, right? It's a goal that you set for yourself. The existentialists tell us that that's the best thing about us. The most characteristically human thing is that we sometimes set our own goals in the face of existential absurdity. So that would be an extreme case of unsupervised learning in the sense of radically deciding based on nothing at all, the existentialists say, what your goals are going to be. So thinking about this unsupervised learning stuff, I'd like you to be thinking about that. So where are these things getting their goals? Are we sneaking goals into them? Are we sneaking intelligence into them? Particularly, a thing that I think is constant throughout this, and I'm giving this to you as a question, but I'll tell you what I think the answer is right now. The unsupervised learning always requires curated data. So that was true in the supervised learning. Remember the stuff about trucks and tanks, right? So if you give it a whole bunch of pictures of trucks in the morning and tanks in the evening, it's going to learn to distinguish them, but only in terms of morning and evening, not trucks and tanks. So you need to give it curated data carefully crafted to get the right kind of learning to happen. And that remains true in supervised learning as well. You still have to pick which data you're feeding it in order to get it to categorize in ways that you like. So these programs, none of these programs so far go out into the world and actively solicit data from the world. That's not a thing that we've figured out how to do with them yet. And think about how babies act. Babies don't just lay there. I mean, for a few weeks, they're just kind of wobbly messes, but like fairly quickly, they begin to actively explore and investigate their worlds. They're not just sitting there waiting for data to come in. They're actively trying to mess with things, and when they get to be 1 or 2, they're actively trying to destroy everything that they can touch to get the most information-rich experience that they can. And what they're doing is curating their own data sets, aren't they? They're trying to get new data for themselves, trying to actively intervene in the world to get it to give them the kind of data that they're interested in. So that's a thing that humans do, that practically every animal, as far as I can tell, does, but that the neural nets are not quite there yet. So they're just sort of sitting there, and we feed them the data. They are not going out and getting their own data. This might be a case in which having a body is crucial to being intelligent, because it's through your embodiment that you explore the world and actively solicit your own data sets, isn't it? Especially as a child, that's what you do. You reach out and grab things, you hold them up to your face and like rotate them around to get the shape of them, right? You move through your environment, you physically move through your environment. So having a body is one of the main ways in which we, at first, do this actively curating our own data sets rather than just passively letting them wash over us. Okay, so things to think about. Where do the goals come from? Where's the information stream coming from? And how should this impact our thinking about this stuff as a strong AI project, right? What would we need to do with these systems to make them like us? And it's not, we don't need to get them to be completely unsupervised because we're a bit supervised, but are they unsupervised enough such that we can see hope for these things as eventually becoming genuinely intelligent agents? Okay. So far, so good? Good. Okay, so right off the bat, I'd like to introduce a distinction between two kinds of algorithms. Notice the semantic drift, the change in the way these words are used. So when I told you about algorithms at during the good old-fashioned AI stuff, I was like, algorithm, you know what that means? It means it either always gets the answer or it tells you that there is no answer. That's what I told you an algorithm means. That was kind of the 1980s version of algorithm. We're now, by this time we're in the 1990s, and it doesn't mean that anymore. Right now, algorithm just means program. So the algorithms that we're talking about from now on, just like everybody's using the word algorithm in this way, it just means program or something like that, okay? So let's talk about two different kinds of algorithm, discriminative and generative. So last time we were just looking at discriminative neural networks. So their job was, the discriminative job is, I give you a bunch of data and your job is to put labels on it, tag it, right? So the Perceptron's job, one of his job was to look at a picture and tell me, is that a mine or a rock? Is that a tank or a truck? So you're receiving data and your job is to categorize it. Basically, it was a categorization task. So that's a discriminative algorithm. There's another kind of algorithm, though, that we're going to talk about today, and it's crucial to the kind of more advanced neural networks that are kind of underwriting stuff today, which is a generative algorithm. So a generative algorithm goes in the opposite direction. It so given a category, it tries to generate some data that would fit it. Yeah, so somebody's tried to generate a balloon version of this famous piece of art. So the two different directions you can go, right? So I tell you, make something that looks like a face, and my generative algorithm produces something, right? Okay. So that's just sort of like running the system in the opposite direction. Instead of doing a category, instead of figuring out the category based on the data, it tries to generate data based on a category. Okay? Okay. So let me now introduce to you the wake-sleep algorithm. Not an algorithm in the sense of Hausland, but it's an algorithm in the sense that it's a program. It was developed in the 1990s by a guy called Geoffrey Hinton, who was or is still at U of T. Is he still at U of T? Yeah, he's still, okay. That's fair. I mean, if I was as smart and famous as Geoffrey Hinton, I would be in hiding too. Because this guy has already done like incredible work. He kind of kicked off the next wave of, so there was a kind of dip. Remember I showed you that Google Ngram last time? Where there's a kind of dip around 2004, stuff sort of fizzling out. The new wave of connectionist research is largely built around the ideas from Hinton. So he made just a titanic contribution to the history of AI. And if I'd done that much work, I would be kicking back and just talking to my friends too. So fair to him. Hinton says of this algorithm, and I quote, that it sounds crazy. That when I tell you how it works, you're going to be like, that's not going to work. That sounds ridiculous. That's not going to do the job that you think it is, but it does. So here's the wake-sleep algorithm. So, and it's got a discriminative and generative phase. That's why I told you about that stuff, because this is the two phases of the wake-sleep algorithm. So it's got a bunch of layers, data H1, H2, H3. Each of those are it's fine to think of them as as a type of neural network called a Helmholtz machine. Doesn't matter, it's a neural network. And what it does is the following. So at first it takes in some data. So the red one is the wake cycle, takes in some data. And it does the discriminative task at H1. That is to say, it tries to categorize it. It tries to make generalizations from the data, right? And then that passes that best attempt to generalize up to H2, H3. The number of layers doesn't really matter. It's just like a multi-layered set of neural nets. Okay, so it's doing categorization of categorization of categorization. It's trying to come up with more and more compressed versions of the data. So it's trying to find the invariant features of the data, the things that stay the same across instances of data. Okay, so that's the wake cycle. It's like being when you're awake, when you are learning things, when you are experiencing the world and trying to understand it. Yeah? Okay. And then once it's done that, it then goes into the sleep cycle. So instead of a discriminative phase, it uses, I think it's not exactly the same equations, but it's equations that share variables. The same layers then try to generate their own data. So it's a generative phase. The sleep phase is a generative phase. So H3 generates what sort of data it thinks it's likely to see and passes it to H2, which then does the same. So based on the data that H3 gave it, H2 tries to generate its own data down to H1. So it takes in some information, tries its best to generalize based on it, and using those generalizations, tries to spit out what it thinks it's likely to see next. And then goes back up and cycles through. So it does a bunch of wake-sleep cycles until it kind of converges, and then you give it some new data. And it does it again. Okay? So that's the basics of the wake-sleep algorithm. So in some sense, what's really going on here is just data compression. Data compression. It's trying to find in some sense, the goal of this system, built into the very guts of the system, is this goal of trying to find the most compact representation of the data that it possibly can. So why do you like data compression? We all like data compression. Everybody loves data compression. You're at a party, you're like, what do you like? I love data compression. No, okay, so why do you want data compression? So here's the simplest example I can think of data compression. You got a bunch of points, little x's, little red x's, and you draw a line through them. So it's much more efficient to represent this data as a line. You just have to tell me what the slope of the line is and where it starts, right? So you can, instead of having to tell me where every single one of those little red dots are, you just one line, okay? So it's a simpler representation. What else does this do for you? Like, this is the basic move of science, right? This is what science does. What else does this do for you? Drawing a line of best fit. Yeah? It tells you the relationship between x and y. Yeah, ideally. So in the best case scenario, what we've learned about is the correlation between x and y. That's really nice. And if you're really lucky, you learned about a causal relationship between x and y, such that if you wanted to manipulate y, you know what to do to x. So suppose x is like like a dial that you can dial up and down, and you want y to be at a particular level. If that's a causal relationship and it's x causing y, then suddenly you have control over y by controlling x. That's a very exciting prospect. I mean, that's the ideal case. A little more modestly, it does things for you like tell you what's happening between the x's. So you got a limited sample, right? There's a limited number of x's. And you might like to know, okay, so between this x and that x, what's going on? Well, that line of best fit gives you some good guesses, doesn't it? Gives you some good information. It's also the case that you're probably going to have a limited set in the sense of it only goes so far on the x-axis or only so far on the y-axis. You might want to know what happens beyond my sample, right? Beyond the x's that I have, what goes on? The line of best fit gives you some at least the possibility of guessing about that stuff, right? So data compression, it's a way of getting at what's invariant in the data, right? And that's what you want. You want to be able to extract from the world those things that stay the same across changes. The world is constantly changing. It's a messy, confusing place. It would be really nice if we were able to say, well, despite all this change, I know what's going to stay the same. The relationship between x and y. Right? This is, again, these are the kind of fundamental goals of science. We want to know when you extract a law of nature, what you've extracted is hopefully something that stays the same across all of the possible changes. So that's nice. So that's basically what the wake-sleep algorithm is trying to get out, is the generalizations of the data. So you're feeding it a bunch of data, and what it's trying to do, and in fact, all of the systems that we've looked at so far, all of the neural networks that we've looked at so far, are basically doing this data compression thing. That's the wake cycle of the wake-sleep cycle. Okay, but then what's the sleep cycle? What's going on? So the wake cycle is doing data compression across several layers, and it builds a bunch of generalizations. It's guesses about what the invariants in the system are. It's best guesses given the data that you've given it. And then it uses those guesses about what the generalities are to produce its own data. So, at first it's not very good. Suppose you give it a bunch of triangles, and then early on, it's going to produce some weird things. It's going to produce some things that don't look very much like the data. It's got some features involved, like they're all green. Many of them have got pointy bits. That's nice. That's a feature that it's pulled out of this data set. But it's not going to match it very well. So it needs a bunch of data to train on to get better and better generalizations. The danger is overfitting to the data. So that was what we saw with tanks and trucks, right? overfitting to the data. So the particularities, the weird peculiarities of the data that you fed it can sometimes be what it thinks is the important stuff. So suppose I give you a bunch of lab reports, and at the top of every one is like, Corey Lewis's lab report, number 7. And I say, here, I want you to generalize from all these lab reports to some law of nature. And you go and you look through them all and you say, all data comes labeled Corey Lewis's lab report number blank. And it's all in Times New Roman. It's all 12-point font and double-spaced. You picked up on the wrong generality, right? You picked up on the wrong thing. Although it was invariant in the data set, it wasn't the thing that was an important generality. So what happens here? So the sleep cycle is in some sense where it tries to break out of overfitting the data, when it generates its own guesses. So the data coming in constrains the generalizations that it makes, and then in the sleep cycle, it opens those possibilities back up again. It unspecializes, it ungeneralizes in some sense. It opens up its space of possibilities for what it's thinking about, and then when the next batch of data comes in, it's got a much wider view of what possibly the generalities it's trying to grab onto are. So it's got a kind of an iterative process. So the early neural networks that I showed you were just narrowing in. They were just narrowing in on what they thought the generalities were. And this one, what we've got is a process of first narrowing in, then opening up, then narrowing in, then opening up, then narrowing in. And this seems to produce, this as a matter of fact, produces much better generalizations, much more robust generalizations, generalizations that are much less prone to overfitting, generalizations that are much more likely to match the ones that are in the world, which is very exciting. This is like a big, big leap forward in neural network training. It's also, by the way, generated, so this is how you know you're doing really good science. Not just good science, but really good science. This also produced a novel theory of why we dream, why we humans dream. And that's why it's called, I mean, they called it the wake-sleep algorithm not because they thought this was actually how we do it, they just called it that. But then people started thinking about this and they were like, maybe that's what dreams are for. So what happens when you dream? It's not that just pure randomness happens, is it? You're not just like, there's a square and there's a dog and it's all just a maelstrom of nonsense. No, it's got a kind of semi-coherence about it, doesn't it? Not as much as your normal waking life, but sometimes. But like, there's a kind of structure. It's a weird structure. It's a structure that's unlike the possibilities that you're used to experiencing while you're awake. But it's a structure. So maybe this is what you're doing when you're dreaming. What you're doing is unspecializing, right? So you've got a bunch of information from your world. Your brain is hungry for finding the invariance in it because it wants to feel safe and in control, right? But you don't want to just grab onto the invariance. You don't want to just narrow down. You want to also be opening up to new possibilities, such that you're not fixated on just a few possibilities that look like they're constant in your world. And maybe that's what dreams are. Maybe dreams are your brain giving itself a little space. It's just playing around. But the play actually turns out to be, these models show us that playing around is absolutely essential if you want to be a robust generalizer, rather than a rigid, fixated on details generalizer. So maybe that's what dreams are. Maybe that's why we need to play. And being playful is actually crucial to being a good thinker. I don't know. So this is a theory, not a well-established fact, but that's possibilities. Yeah?
I think it could also relate to why people, all their goals
Why they call their goals their dreams. Interesting, interesting. Yeah, maybe, yeah. So why do we call our goals dreams? Like, I want my teeth to fall out and to be late for a lecture. Actually, you know those dreams where, just so this is an absolute aside, but you know those dreams where you're late for class and you didn't study for the exam? I'm happy to say that I've finally graduated from those. So last night I had a dream where I was late to teach a logic class and I didn't set up the recording for the video. So now I'm having school anxiety dreams, not about being in class, but about being the professor. Progress, hooray. So yeah, so it's weird, given that our dreams are like that, it's weird to say that our goals are like dreams, but maybe that's because what they are, our goals are like possibilities that seem to be beyond just the ones that exist in your world already. Interesting, yeah. So how much is ideal or how much as a matter of fact we do?
Like, how would this work? Like, how do you not get to the point of like, okay, I'm dreaming too much and kind of...
Yeah. Very good question. So are you asking, so there's two questions you might be asking, one about the wake-sleep algorithm and one about us as humans. So the wake-sleep algorithm, I take it that it's, it does, so it's just like you can measure how much you're converging. So like there's diminishing returns. So when you pass some point of diminishing returns, you're like, okay, that's enough.
Do you think for like backpropagation for how much dreaming you do?
Something like, well, there's a, yeah, so like how much is the change, given how much computational time you're spending, how big is the change on this cycle? And after some point, you're like, okay, that's enough. For us, I have no idea. But it is clear that, so what's clear from psychology research is that dreaming is biologically very important, but nobody's been able to work out why. Like you don't dream all night long. Many parts of the sleep cycle involve no dreaming, but for some reason, dreaming seems to be important to us biologically, and it has been very unclear why that should be the case. I don't know, maybe here's a thing. Maybe here's an account, because your brain, while you're awake, you're working really hard to generalize from the data that you're being given, so you don't have to worry about every single tiny little thing that happened throughout your day. You just get the general gist of it, and therefore have some hopefully causal control over your world, and you can know what to expect and all that stuff. But then if you're just doing that, then you get rigid and overly focused. And what you need is the cycle of opening back up. This is why you need sleep if you're going to do anything like intellectual work. You need sleep. Yeah?
Just like thinking about how there could be like a constraint on like how far we do the cycle of like
Right.
constricting.
Yeah.
When humans sleep, like we go through the pattern of like sleep state and then we wake up
Right.
without remembering that we woke up and
Right.
then fall back into sleep state.
Yeah.
So do you think that potentially it could be that, like this is
Oh.
hypothetical,
Mm-hmm.
but that we do reach like a max for like dreaming and exponentially like thinking that wide to the point where we wake up and then our brain resets, we go back into sleep state and we keep exploring.
That strikes me as entirely possible. That sounds plausible even. Yeah, so maybe, yeah, so you'd have like several in and out of sleep, in and out of deep sleep, in and out of REM sleep where you dream. So maybe it's like, okay, I've got the most that I can out of the REM sleep cycle. And then notice that's entirely consonant with what most people report happens. So if you actually wake up during the night, what happens? What's going on in your mind? You're thinking about your life, aren't you? Right? You're thinking about your life in a fairly broad sense, aren't you? Like, you're not just like, oh, my bed is so comfy. You're like, I wonder what I'm going to do with my existence. So you're having these like broad picture like thoughts, which seem to be the generalization stuff again. So you move to the generalization phase, try to reconsolidate your picture of yourself and your world, and then your brain's like, okay, cool. Now we got some more to work with, back into the opening up stage. So you do a narrowing down phase of like, who am I and what's my life about? And then you go back to sleep and you open back up again. So that sounds very plausible to me. More studies warranted. Yeah. As they say in psychology all the time. Yeah. Yeah.
Is this kind of like a thought of like an offline gestalting or attention?
So in some sense, it's the maybe.
This seems very similar to attention. Like you're instead of like holding in, it's kind of like a forced read.
So I think it's interesting, but the relationship is a bit convoluted because in some sense generalizing is gestalting. In some sense the wake cycle is when you're putting it all together, and then the dreaming cycle is when you're taking it apart again. So you're imagining, what would my life be like if I didn't have a mouth, or like if I lived on Mars, or so you take the part in a dream, you take the parts of your life and kind of imagine them reassembled in some totally different gestalt. So in some sense, I would say that it's instead of putting it all together in dreams, you're taking it all apart again. The wake cycle is when you're putting it all together in some coherent, fixed picture. And notice how dreams often have this quality of they don't make any sense. The parts that when you wake up, you're like, well, it was my house, but it wasn't my house. My girlfriend was there, but she wasn't my girlfriend. And I was me, but I wasn't me. The parts don't necessarily cohere with each other in any good way. And in the dream, you're fine with it. But when you wake up, you're like, well, that didn't make any sense, did it? So it could be the case. I think it might even be the opposite, that the gestalting phase is the wake cycle. And the deconstruction of the gestalt is what happens in the sleep cycle. Yeah. You all need sleep. If you're not sleeping, you're not thinking properly. Sleep is work. Go to sleep. Not right now, but like, I don't know. I'm horrified when I hear stories of students doing repetitive all-nighters. I think maybe there are skills you can learn under those conditions, but they're not the skills that I'm trying to teach you here. And they're not that's bad. That's bad. Don't do that. Don't do that. Yeah. Okay, briefly. So this was in like the 90s that we came up with this. Jeffrey Hinton and co. came up with this. There's been some really interesting developments since then. So for example, let me show you briefly. Generative adversarial networks, which is in some sense the same basic idea, but a little bit of a different architecture. This portrait of Edmond Bellamy sold for $432,500 at Christie's auction house, the most prestigious art auction house in the world, in 2018. And it was produced by a neural network. What they did was fed it a whole bunch of classical art and generated this thing. Yeah. It was some I think it was literally like high school students that did this. Like it was students in any case, a group of 3 people. Probably you couldn't, I don't know. This might not be a good career path, like if you're thinking about this, because it's the first one. But so let me show you a little bit about the system that produced this. So it's what's called a generative adversarial network, and it's got 2 separate parts. So the wake-sleep algorithm, you're kind of passing it through roughly the same network or deeply related parts of the same network. A generative adversarial network works like the following. So you've got a generator network that's doing a generative cycle, right? So you're feeding it, first of all, you feed it just some randomness. It goes into the generative network and produces some fake images. And then those fake images, along with a bunch of real images, are fed to a discriminator network that's doing the discrimination task. And that discriminator network tries to guess whether the thing that you fed it was a real image or a generated image. Okay, so, and then what it does, is cycle this over and over again. So you tell at the end of it, this is in some sense still backpropagation of error. You tell the discriminator network whether it got the answer right or wrong, and then you tell the generator network whether it fooled the discriminator or not. This is a kind of cops and robbers scenario. Imagine the generator network is trying to produce fake $20 bills, right? And the discriminator network is trying to tell whether it's a counterfeit, or a real 20. Okay? So you've got these 2 neural networks competing against each other. one of them trying to produce as realistic images as it possibly can, and one of it trying to discriminate whether the images that it's getting fed are real or fake. And you just play them off each other. You have them fight. You put them into competition with each other over and over and over and over and over again, and they both get incrementally better over time. So they're just getting better and better. The generator network is getting better and better at fooling the discriminator, and the discriminator is getting better and better at not being fooled by the generator. So you basically built two robots and made them fight. Not robots, but. So this is notice that this is a little different than the wake-sleep algorithm where it's kind of the same network talking to itself. This is now two neural networks fighting against each other. And they produce some really good stuff. This is one of the architectures. So there's a bunch of modern architectures that are in variations of this. This is one of the architectures that does things like deep fakes. Have you seen these like auto-generated faces? Scary. Okay, I'll find this on the internet if you haven't seen this and show you after the break. It's scary how realistic they are. So this type of architecture is what underlies that stuff. Just before the break, does anybody know what the deep in deep learning means? It literally just means way back in the 80s, hidden layers. That's all deep means. When they say deep learning, you could say that about the ones from the 80s. Anyway, but deep learning plus doing things like the wake-sleep algorithm, plus doing things like adversarial networks, then you've got what's basically the contemporary version of neural networks that do the kind of impressive stuff that we've got right now. Okay. We've been talking about semi-supervised learning. I think we shouldn't sort of be very rigid about completely supervised, completely unsupervised, right? So the wake-sleep algorithm, it's trying to generate something that is generalizable, right? So that's, in some sense, it knows what it's after. In some sense, you told it what it's looking for. And again, even with a wake-sleep algorithm, you're the one feeding it the data, right? The data is not just coming out of nowhere. It's not just wandering around the world getting its own data. You're the one that's giving it the data that's appropriate to learning the thing that it's trying to learn. You feed it faces, and it learns how to look at faces. You feed it handwriting, it learns handwriting. You can't feed it faces and handwriting. It'll just choke on that. It will produce monstrosities. Generative adversarial networks. Again, this is a semi-supervised learning because you have to tell the discriminator network whether it got it right in terms of spotting fakes, right? So you're telling it success or failure. At the same time, I think this is in some sense, less supervised than the original neural networks that we were first talking about. Let's move on to talk a little bit about semi-supervised or unsupervised plasticity. So remember we talked about one of the ways that you can keep your neural network from falling into a rigid way of categorizing the world is to shift around the nodes. And here's a sense in which you can get that to happen in a semi-supervised way. I talked about it in literally just people going in and knocking out nodes or adding in nodes, but here's an algorithm that does that in a automated sort of way. So proposed in the 1990s, and it's a system in which new neurons are added during the training process. So here's the steps that it goes through. Phase one, empty network. It's not doing anything, it's empty. And then you add some neurons. So add a couple of neurons and don't let them do anything yet. So you let them listen in on what's happening and figure out what they would say, but you don't let them say it. So you let them accept input and do their calculations, but don't let them put information back into the network yet. And then, so after some training cycles, you say which neuron's activity most correlates with the error signal. So again, you need an error signal, you need some feedback, so it's only semi-supervised, or it's at least semi-supervised. But suppose you've got a few neurons in place, you add in a new one, you let it listen in, you let connections go into it, And then the one that is most, so the activity of that neuron is most correlated with the error signal coming out. So, oh, this one looks like it's saying the same things as the error signal. That's interesting. And the one that's most correlated with the error signal, you then let it interact with the network. You let it put feedback into the network. So let it have its, not just listening anymore, it's having it say. And if that increases the error signal, then you kill it. You make it not be allowed to be in the network anymore. But if it decreases the error signal, then it gets to stay. So you let it listen, you see whether it's correlated well with the error signal that's coming out of the network, and then if letting it interact reduces the error signal, then it gets to stay and participate in the network forever after. And you go back and add a new neuron, let it listen, see whether it's correlated with the error signal. If it is, it gets to participate. And then if its participation helps, it gets to live. If it doesn't, it gets eliminated. And you do this over and over again, adding neurons and seeing what they do, basically. And if they help, they stay. If they don't, they have to go. It's very grim, but yeah. Sorry.
How do you decide where to place or where to remove the neuron?
So you just add them randomly. So it's random additions, and then you randomly add a bunch that are just listening, and then whichever ones are most tightly correlated then get to at least try their hand at participating in the network. Yeah. From the perspective of neurons, very grim. But as a matter of fact, this is a fairly efficient way of quickly getting a neural network that's reasonably well trained. Sorry. Okay, so semi-supervised. You need an error signal, but you can do some fancy stuff with this that makes it less of a supervised. Sorry, yeah? So it's you do a random placement, that is to say it randomly gets connections in and connections out. So like maybe if we hook it up here and there, let's see what happens then. So you're really just trying stuff and seeing what it does. Yeah.
Wasn't that heuristic kind of bad?
So as a guess and check model heuristic, that's right, unless, so the guess and check heuristic is a terrible, terrible heuristic most of the time, and that's because most of the time the space of possible moves is poor in solutions, in good solutions. Guess and check is perfectly fine if the space that you're guessing in is rich with solutions. So if there's potentially good solutions all over the place, guess and check is perfectly okay. So I think what this tells us is that there are lots of ways that you could hook up a new neuron that would incrementally help it. And notice that there's no possible way that your brain has all of its connections pre-specified by genetics, because you've got 30,000 genes or so and trillions of neural connections. So guess and check is in some sense, guess and check with feedback. So it's more than just random guessing and checking, it's guessing and checking with feedback. Also the way evolution works, by the way. So like, evolution is a very messy guess and check game where like, hey, I wonder if this mutation will help you survive and thrive. Nope, sorry. Try again in another million years. Yep.
So this is more so kind of like where and how many neurons I need rather than the connections between them?
Well, so it's both. So you're adding them to random layers and you're adding random connections in and out, as I understand it. Yeah. So one of the interesting things about these systems is that they seem to They seem to go through kind of developmental phases the way we do. So I'm sorry, I could not find the citation for this, but as I was told the story, you can give one of these things a task like try to figure out what the equation for distance is. So velocity times time, right? So velocity times time equals distance. We're all good with that. So there's 3 variables, and its job is to try to figure out that equation. And it'll go through kind of phases of development. So first it'll try out, hey, maybe it's just whatever the velocity is, that's what distance is. So 100 kilometers an hour for 2 hours, you went 100 kilometers. And so that doesn't work. Then it will go through just adding up. So that's one phase of its development. Then it'll go through just adding up time plus velocity. So 100 kilometers an hour plus 2 hours, 102. Maybe that's the distance that I traveled. And then it will go through, eventually get to multiplication. So it'll get to multiplying time times velocity, which is the correct answer, right? So that kind of developmental phases suggests that it's in some sense developing new capacities as you add neurons. It's not just incrementally changing what it does. It can actually learn how to do new things in some sense. In similar ways, and that's apparently quite similar to the way children acquire the notion of like understanding distance times time equals, velocity times time equals distance. So we go through similar developmental phases. I don't know. The thing to notice perhaps is that this system is in some sense self-organizing, in some broad sense. That is, we're putting constraints on it, but within those constraints, it's working out how to organize itself, which is quite different than the way we were doing things in the good old-fashioned AI scenario, right? So there's nothing in principle that says a GoFi machine can't be self-organizing in the sense of changing its own programming. But that's, as a matter of fact, not how anybody wrote these things. Probably because, there are no self-organized computer programs, as far as I know. Because if you get one line of code wrong, they just crash. So these neural networks are still single domain, single problem solvers, generally speaking. And we still have to really kind of shepherd them towards the right answer. If they're going to get the right answer, it's because we created exactly the right conditions for them to do that. We picked the right data set for them. We fed it to them in the right order. We wrote the right algorithms. We tinkered with them until they dealt with the data in the appropriate ways. So in that sense, they're still quite far from the dream of strong AI. But nonetheless, yeah.
Kind of a question with the Cascade networks, is there also a preference for kind of the fewer processing elements, the better? You want to have as few nodes, the way that they're ordered, the structure of the layers, and how they're set up.
Not that I know of. I don't believe that there is. There's, of course, you might add that in. You might say, well, I'm not going to do this forever. I'm not going to just keep adding neurons and neurons and neurons. But as far as I know, that's not built into the system.
You could add, let's say, more neurons in the first layer and achieve the same result. Let's say you took 2 neurons away and kind of reshuffled or added a neuron in the fourth layer and get the same performance, but still have overall less neurons. Does that factor for that? Is that programmed in?
I don't believe it is. But that does seem to be how our brains work.
Yeah.
So for example, if a neuron's not doing much, so neurons in some sense, your actual neurons have to, it's a real libertarian capitalist nightmare in your brain actually. The neurons that get to do a lot of stuff and that have a big impact on neurons near them get more food. They get more resources and they get to grow more connections. And the neurons that don't seem to be having a big impact on the neurons around them kind of just go away. In some sense, it's like neural Darwinism happening in your brain. It's rough being a neuron. Yeah. But this should make sense to you given everything we've talked about the fact that you can't spend an unlimited amount of resources thinking, right? There's really heavy constraints on how much metabolic energy you can spend. I'm sure that I said already, your brain consumes 20% of your calories and weighs 5% of your body. Like, so your brain is this really energy hungry organ already, and it's already large and very sensitive. Like, your brain is like the consistency of soft butter, and it's really damage sensitive. Like, you can lose half your liver and it just grows back. Your brain it's easy to damage, it's very sensitive, it's very metabolically hungry. It's one of the biggest challenges for childbirth. So like unassisted childbirth, something like 1/4 of the time either the child or the mother dies, because we've got these hilariously enormous heads. It's really, there's a lot of downsides to having a brain already as big as the one that we have. So there's a lot of pressure to keep it from getting any bigger, right? You can't just let it get, I know the science, like, I don't know what those alien science fiction aliens with like huge, humongous heads are doing. Probably cesarean. Like that's the only way that, or like tubes or something. They're growing them in vats. I don't know. So yeah, the point about like how do you pare down neurons biologically? That's a really serious question. So if that's not part of the cascade correlation model, if we're trying to make it a more realistic picture, one of the selling points of these things is supposed to be biological plausibility. So if we're trying to create a biologically plausible model, you're going to want to include something about like, don't add in too many neurons. Yeah. Okay. So some advantages of this stuff, like, as I was just saying, they're much more biologically plausible, right? I mean, not completely, they're not identical to brains. Again, the missing neurotransmitters should concern you. It's also the case that, so in the 80s when we started designing these things, people thought of neurons as a lot like electrical signals traveling through transistors. Like, it might be just that an individual neuron firing carries information. Current thinking about how neurons work is much more like it's collections of neurons firing in synchrony that is carrying information, and the degree to which they're synchronized or unsynchronized is how the information is transmitted across the brain. So much less like one neuron, these neural networks is just like one neuron firing to another neuron is the unit of information transfer. Whereas in your brain, probably not so much. Nonetheless, it's more plausible than the GoFi guys were, right? Really hard to see how you would get a Turing machine going in your brain. It's hard to see anyway. Another kind of nice advantage of these things, they display what's called graceful degradation, which sounds like a goth person slowly wilting in the sewers of Paris. But okay, so notice the following. If I turn down the lights in this room, you can still sort of read. You can still see people's faces. Turn them down and down and down. It's not that there's no just cutoff, right? It's a slow, steady, the less you can see, the less information you can pull out of the environment, but it's a slow, graceful degradation. If you lose a couple of brain cells, you're kind of okay, right? You can have, actually, I just talked about how sensitive our brains are, but the fact is you can get your head knocked around pretty good and still do calculus, right? I'm sure, I would be astonished if anybody in this room has had zero head trauma, right? You don't get to be a toddler and have zero head trauma. So we've got some degree of tolerance for damage. We've got some degree of tolerance for insults and all that stuff. And what happens is maybe your performance goes down a little. And compare that to your computers, where it's like, if you start pulling out parts of the computer, what happens? It just gets a little slower. Still running Skyrim, it's just not getting the 60 FPS. No. you pull out irrelevant parts until you hit one that matters, and then it's done, 0, right? Also probably a reason why we don't let computer programs, in the normal sense of computer programs, self-organize, right? You don't let Microsoft Word tinker with its own programming, because one wrong line means the whole thing comes crashing down. Whereas neural networks seem to have the same property that we do, which is their performance degrades gradually. So if you do, and lots of interesting studies where you knock out one neuron in a connectionist network, and if it's got if it's got 10 neurons, that's disastrous. But if it's got the usual like hundreds or thousands, knocking out one doesn't do that much harm to it. It will decrease its performance, but it won't take it to 0. Yeah.
I think there's something called neural network pruning, which actually improves.
Right. Network pruning. Yeah. So in some cases, it can actually make the performance better. If you knock out, presumably you knock it out and see what happens. And then if it gets better, you're like, okay, we didn't need that one. Yeah. Imagine doing that to your laptop. I'm going to pry out this part, see what happens. Oh, that didn't make it better. Jeez, what a surprise. Yeah, so they've got this property of graceful degradation, which is what we've got. So that's nice, right? That's a nice property for these things to have. Gives you some hope that they're operating something like the way we are. They also are really good at doing this thing called simultaneous constraint satisfaction that we talked about way back in psychology. Remember the cat, where the H's were where the H and A were identical? That was simultaneous constraint satisfaction. You have to be able to read the word to read the letters. You have to be able to read the letters to read the words. And if you are a linear logical processor, that is very, very hard for you to do. If you're doing things in a stepwise fashion, getting 2 constraints satisfied at the same time is incredibly difficult. These neural networks can do that fine. They're just fine at it. There's no problem. Yeah? They're also good at, in a kind of related fact, procedural tasks. So, you know what's super hard for a Go5 program to do? Catch a ball. Catch a ball. You know what we're really good at? Throwing and catching things. Yeah? And why is that? Well, for one thing, the Go5 is probably not, so we didn't talk at all about timing in the good old-fashioned way. Do you remember anything to do with timing in that whole section? There was nothing. There was nothing about the dynamical quality of this thing, right? And dynamics is a constraint that you have to solve at the same time as other constraints, like getting under the ball, positioning yourself under the ball, getting your hand in the right place, right? So things like procedural knowledge, like catching a ball, riding a bike, riding a longboard, those are skills that require massive simultaneous constraint satisfaction. And there's things that a Go5 machine, they are terrible at this stuff. And to the extent that we've got robots that are any good at all, it's because they've got neural networks built into them. Neural networks gave us way more hope of being good at that stuff. Remember Shaky? I wouldn't want Shaky on my softball team, right? Right? Shaky was calculating in a very abstract way where to move and how to do that. Whereas a neural network can do it in a kind of smooth, procedural sense. So if we're thinking about how is it possible for us to have procedural knowledge, neural networks give us a much better picture of how that could be possible. And like a more clear relationship with development. We've been talking about how you get one of these things to grow and to change and to adapt. And that's what the good old-fashioned AI people thought was irrelevant to understanding cognition. They didn't care about that stuff at all, did they? I'm told that in the good old-fashioned AI days, when they talked about developmental psychology, the psychology of growing from a child to an adult, they thought the story went like this. Baby plus delta baby equals adult. The end. Change over time plus babies. That's the story about development that we need. And it's just utterly impoverished, right? I think we talked about how, I hope we talked about how, like if you want to understand how your laptop works, you really don't need to see the factory, right? If you want to understand how Microsoft Word is instantiated on your laptop, seeing the process by which your laptop was produced isn't that helpful. It might be a curiosity, but it's not central to the project of understanding it. Whereas a connectionist network, the whole developmental process is built into the way we are understanding these things, right? They are objects under change, and the fact that they're as malleable as they are is part of what makes them good, right? So instead of trying to program the answers into these things, so the GoFi picture was, we know the answers, it's logic and math, we're going to program that into you with some classical definitions, and you're going to think through it by me telling you the answer. Connectionist networks seem to be opening up the possibility of not telling them the answers, but teaching them how to grow, teaching them how to take in information and deal with it. So again, this is why the Psych project is a little bit tragic, because the Psych project was precisely, let's program in common sense. Let's program in the answers by hand. And current deep learning stuff takes the developmental approach. That is to say, I'm going to build something that's capable of learning and then just feed it the world, like you all did, right? Evolution made you capable of learning and basically just a big open space for learning. You know, gives you some hard, like being capable of learning is an incredible feat. It's not like you just, any lump of matter is capable of learning. So being a baby that's capable of learning is an incredibly delicate and amazing task for evolution to have solved, but it didn't solve the task of making you an intelligent agent exactly. It made you able to become an intelligent agent. So there's a kind of shift in the relevance of development that goes from the GoFi view to the connectionist view. So that's another quite exciting development, quite interesting way of changing the way we're thinking about AI. We made it dynamical, we made it adaptive, we made it flexible. It's good, it's good stuff, right? Yeah.
You don't need to have like a neural network to be adaptive though, right? Like you don't need to have like a connection system to still be dynamic.
That's right, that's right. And in fact, we're going to talk in so-called third generation AI. Maybe there's different architectures that you could think about. But so a good old-fashioned AI computer can be adaptive in some sense, but adaptivity wasn't it wasn't the focus, and it wasn't sort of the basic architecture of the thing. Whereas with a connectionist net, it's the very guts of the thing is a learning machine, rather than a set of rules for how to be rational. Yeah.
It's just if I were to program a game of chess with a GoFi kind of approach,
Yeah.
it would memorize every move that I had ever made or every player that I had ever played, and it would just make a database.
Mm-hmm.
This is the board position, these are the rules that the player made,
Mm-hmm.
and it would then cross-reference like what move should I make. Like it still is learning, storing data.
Sure.
Kind of generating.
Yep. I mean, you're right. You're right. It's not that the GoFi excludes learning, but it's not. This I hope that it's clear that this is it's a different kind of learning. That is the very architecture and the kind of. I love that one of the reasons I wanted to show you the Cascade correlation model. It's a bit of an old model, like it's not cutting edge, but the whole thing here is that it's not just learning, but remaking itself from the ground, in some sense from the ground up. So reconstructing its own internal structure is the way that it learns, rather than thinking it already knows what the right learning algorithm is. We say, I'm going to teach you how to learn, right? So this thing is reconstructing itself in a way that makes it more capable of learning. And that's, I mean, I take it that that's your whole education was that. So in primary school, you learned how to not hit each other, and then in high school you learned how to sit down and shut up, which is a crucial skill for learning. You absolutely need to learn to, but you could have learned everything you learned in high school on your own curiosity and interest, probably in about a year, right? Like you spent 4 years. If you were motivated to teach yourself all that stuff, you could have done it much more quickly and efficiently, but you needed to learn how to sit down and shut up. And now in university, what you're learning is how to teach yourself stuff, how to do research, how to do your own research, how to generate your own research program. So learning how to learn is the fundamental thing that you're supposed to be learning. You could have Googled all this stuff yourself, right? I'm working with the same Google all you are, right? What you're learning here is not these facts, but how to learn facts. So I'm giving you the minimum structure possible to scaffold your own capacity to teach yourself. So that seems like it's much better represented by this kind of system that restructures it. The whole point of this is to restructure itself. Whereas a big database, you're like, well, the structure of the database has got to be laid out, it's typically laid out in advance. And you're just filling in a big Excel spreadsheet with the structure, pre-specified structure that you were filling out in the GoFi. That was at least how they built those architectures.
The rules to fill out the database itself don't change, don't when the database.
That's right. That's right. Yeah. So it looks pretty good, right? Looks pretty good. Okay. Now, let's knock it down, shall we? Well, there's no robot. There's no intelligent AI yet. You know this can't be the whole story, right? We got up to like 2009. Okay, so now what I'd like to do is take a little step back and talk a little bit about this argument from 1988 from Jerry Fodor and a person with the most science fiction name I've ever heard, Xenon Felician. That's an awesome name. I sometimes am sad about how bland and white my name is, but I will definitely if I have kids, I will definitely give them the Lewis name because that's cash money. That's worth statistically speaking, having a name as white and boring as mine is worth cash money. So, Jerry Fodor and Xenon Felician, they give us some reasons to think. They give us a really good argument, actually. This is a really powerful argument, I think, about whether connectionism can do some of the things that we think are crucial to cognition. Some human-level cognition stuff that is really important. And this argument mostly hinges on the question, what's the right level of analysis for thinking about cognition? So on some level, I think everybody agrees that we've got a neural network in our heads in the literal sense of a network of neurons. So sure, even the GoFi people would have been like, if you ask one of the classic GoFi people, have you got a bunch of neurons networked together in your head? They'd be like, yes, obviously. I've done Psych 100, I know that. That's not the question. The question is, what's the right level of thinking about this stuff to understand cognition? And of course, we talked about how you can have a neural network instantiate a Turing machine, right? So if you wire your neural network up just right, you could get it to run Minecraft, right? So, and furthermore, you can get a laptop to run a neural network. So the question is not, is there a neural network in there somewhere? The question is, what's the right level of explanation? So scientists tell very different causal stories at different levels, right? You could talk about the literal quarks that you're made of. You could talk about you as an organism, as a living thing. You could talk about your place in the ecosystem. You could talk about us, our position in the galaxy. And there's very, very different laws and models and explanations at each of those levels, yeah? So as a collection of quarks, I follow the rules of quantum mechanics I try my best to follow the rules of quantum mechanics, you know? Try not to violate the Pauli exclusion principle, that kind of thing. As a living thing, I follow the laws of biology, right? As a thing flying around the sun, I follow the laws of relativistic physics. And those are very different stories. Those are very different ways of understanding the exact same system. So the question is, if I want to understand me as a cognitive agent, and you and all of us as cognitive agents, what's the right level of explanation? It's not, is there a neural network in there somewhere? It's, is that the right level at which to understand the thinky bits? So for this debate to go, let's set up this assumption. Both Fodor and Felician and the connectionists that they're arguing with, so Fodor and Felician are trying to argue with the connectionists. The connectionists are being like, your GoFi stuff is garbage, our connectionist thing is the way to understand cognition. Both of these groups, however, agree that the mind is in some sense representational. So representational in what sense? It's that you've got, so if I say, here is a bottle, I'm using my mind to represent the bottle. There's an aboutness, right? My thought is about the bottle. So that's the sense of representationalism that we've got. And they both agree that the cognitive level is the level at which you find representations. So that's the shared assumptions. These assumptions are questioned quite heavily by people that come after this. So after this debate, there's people who argue that the mind is not, that cognition is not fundamentally representational. But for the sake of today, and for the sake of understanding this debate, let's just assume that cognition, the cognitive level, is the level at which representations happen. Is that okay? Okay, so anytime that you're debating somebody, if you and them agree on something, that's a good starting point. Actually, you can't argue with somebody unless you agree on most things. This is why it's so astonishing to be on the internet, because people try to argue by disagreeing as much as possible, whereas that's not how arguments work. Arguments are premises that lead to a conclusion, and you have to agree on some of the premises to get them to agree to your conclusion. So this is a premise in the debate. Both sides agree on this. Here's where they disagree. So this is Fodor and Felician. In contrast to GoFi, connectionists propose to design systems that can exhibit intelligent behavior without storing, retrieving, or otherwise operating on structured symbolic representations. So the disagreement is about whether the cognitive level involves structured symbolic representations. Here's a chart from linguistics. The sentence, Watson did not solve the case, broken down into its grammatical structure. Yeah? Why is this? Okay. Yeah. Okay, so the structural part is the part that they're going to pick on and say that it's very difficult to see how a connectionist network could encode structure. Right? So the GoFi thing is, what is the mind? The mind is a linguistic manipulator. It manipulates structured language-like representations. The GoFi people said, remember we started with the saying, that's not what the mind is like. The mind is not basically operating on language-like objects. So, but what does that do to you? What does that leave you with? So consider the following two sentences. John loves Mary, and Mary loves John. Now, we're all happy with the idea that those are different sentences, right? They have different truth conditions. Much of human life would be different if those were the same sentences. Much of television would be much less interesting, right? So a great deal hangs on the difference in truth value between John loves Mary and Mary loves John. Okay. So we agreed that the representational level is the level of cognition, right? That's the level that we want to understand, the level that we want to explain. For GoFi, representing the difference between those two is easy. It's really easy, right? Because it's manipulating language-like sentences. And those sentences in language break down differently. John is the subject and Mary is the object of the first sentence. and Mary is the subject, and John is the object of the second sentence, right? Or did I get that backwards? I might have got that backwards. So John loves Mary. John is the one doing the loving. Mary is the object of the loving. Yeah. Okay. So go phi, no problem. We got this. Totally easy. Yeah? But if a neural network has a node for John and a node for Mary and a node for loves, and they're all three active at the same time, what disambiguates? What helps it tell the difference? Those three are all active at the same time. What makes one version of it, all three being active, John loves Mary, and what makes one version of it, Mary loves John? Yeah.
The enormous number of other nodes that would presumably be involved with which to contextualize those three.
Ah, interesting. Interesting.
I don't think there are very many neural networks that try and solve problems like this with three nodes.
No, probably not. Probably not. So you might do something like the following. You might say there's a node for John agent and a node for Mary patient. Is that the kind of thing you had in mind? Or because you're not allowed to just say, well, there's a bunch of other stuff happening. You got to give me some story about how it actually instantiates the disambiguation.
I'd have to use training, which is.
You're right. That's true. A true sentence. You would have to train it somehow to disambiguate. But then the question is, how in the machinery of a neural network do you disambiguate the sentences?
Very little working knowledge of neural networks. I feel like a sufficiently trained neural network could somehow figure out the implication directions of the sentences.
So something like this.
Yeah.
Okay.
Or you implement a Turing machine on the neural network, and it's just like a P implies.
Aha. So that's what they're trying to get you to say. That's what Fodor and Felicia are trying to get you to say. They're trying to coax you into wanting to say, yeah, well, just make it do a Turing machine. But then what happens then? Then they win the argument, right? Because they say, no, they force you to say that actually at the level of cognition, what you're doing is computation. Yeah.
I was thinking about this from the Turing machine standpoint, but like if you make this even nastier, John loves John.
Yep.
If there's two different Johns, or versus John loving himself, the system has to be able to still somehow distinguish that one John is distinct from another John,
Yep.
or that John likes himself, or I guess likes himself.
Yeah.
Symbol likes himself or something.
Yeah.
That would destroy kind of Fodor's argument, because you need more data to distinguish between John 1 and John 2, or John 1 likes John 1, or John 2 likes John 2.
Why does that destroy his argument? Because
Like
so.
in this sentence, if you were just simply shoving John loves John
Uh-huh.
into like a formal system,
Uh-huh.
unless it has a way of knowing that other John is different than the original John.
Well, you just say John sub 1 and John sub 2.
That's what I'm saying. You need more data for that. Whereas like
That's fine. But you just told me how a GoFi machine would do that.
yeah.
You just told me how it would do it. So you can't say like, oh, GoFi can't handle two people with the same names. No, it can handle that fine.
Again, like, if you make the argument that you need like a special node for a certain type of John, like John 1 and John 2, that argument still carries over to the GoFi system. You still have that problem. You need John sub 1 and John sub 2.
That's fine though. That's fine.
Then like how can they say that like a Turing machine solves this?
Because it says you would just have different names. So presumably there's more. You say John Tory loves John Stamos, right? Okay, let me get deeper into the argument, and then let me get deeper. So here's one possibility. You want to say you want to add a node. You got a node for John agent and Mary patient. So John agent loves Mary patient. So you got John agent active, loves, and Mary patient active. Hey, that's a thought, right? That's a possibility. Now what about this sentence, they say? John loves Mary and Bill hates Sally. So now we've got John agent and Bill agent, but the ambiguity is back. So now we need John agent loves Mary patient to be its own node or collection of nodes. It doesn't have to be just one node, but like, so John loves Mary and Bill hates Sally. That's not a really hard sentence to parse, right? Nobody crashed on that. But now how many nodes do you need? If you got a node for John agent loves Mary patient, how many nodes do you need to navigate your ordinary life? Yeah.
Don't we have trillions?
Yeah, that's not going to cut it. It's not even going to close to cut it, because the number of sentences you can produce is vastly larger than trillions.
But our trillions are somewhat dynamically allocatable. So
Yep.
you can take some John nodes when they're not being used and turn them into Bill nodes.
Well, what makes them at that point John nodes?
All I've come up with is evolution, so
Okay.
there's no idea.
So what they're trying to force you to say is the following. We'll just add some structure. Let's add some structure to the representations, right? We'll add logical structure. Instead of just having these things be coactive at the same time, that's silly. Don't just make them coactive. Add some logical structure to your representations, because that's how you parse it, right? When you have John loves Mary, you say, this is a structured representation. John is the agent of that sentence, and Mary is the patient. And now they have you in their dialectical grip. Because what did we say is not the way your mind works for connectionists? It doesn't operate over logically structured representations. That's what they said they were rejecting. That's what they said was their whole big thing, was they're going to dump that as the basic operations of the mind. So if you say this, Fodor and Felician have you. You have to admit that the mind is doing computation. Yeah?
But does that then imply that everything that we process has a logical meaning? If you have a sentence that has no logical meaning, or is just a bunch of nonsense, how would you design a logical system?
So you don't need for their argument to work, you don't need it to be the case that everything has got logical structure. They just need to show that you need logical structure. Actually, you're kind of on the edge of
John was John. If you start ruining the logical structure, then you need to add more detail to fix it. You need to add more logic, add more John specification or whatever.
Well, the name, I feel like fixing references is not that hard. Okay. So I got a little bit more. Do you want to take a break and do the rest, or do you want to plow through? Hands up for take a break. Hands up for plow through. All right. There was at least 50% of you were indifferent, but that's okay. Plow through wins. All right. Okay, so the deeper version of this argument. There's a deeper version of this argument that maybe doesn't fall to some of the sort of the specifics that we've been worrying about, is that human thought and language have the following 4 properties, and it's really hard to explain how they work unless you're talking about a system that deals in structured, logically, linguistically structured representations. You got productivity, systematicity, compositionality, and inferential coherence. So let's talk about these things. Productivity. By this they mean the capacity to generate basically an infinite number of sentences. Productivity is the fact that you can always add an and or an or, a negation. You can just keep going. The ball and the bat sat on the mat, which Stephen laid flat in the cold laundromat beside pictures of a cat who once hissed and spat at the forever, right? So there are limits on the length of a sentence you can produce, of course. Those limits are attention span, time, you get hungry eventually, right? But notice this. So if I give you food, pencil, and paper, and pay your rent, those things massively expand the length of the sentence that you can produce, right? If I said I'm going to give you $10 million to write the longest sentence that you can, and has all the resources that you want, how long of a sentence would you write? A long sentence, right? real long. And in some sense, this makes it look like, so remember the Turing machine, right? You can expand a Turing machine's memory just by adding more tape. The tape is the memory, right? You can increase its capacity to deal with larger, more complex representations just by expanding its memory capacity. And you can do that separately from expanding its processor. So processing and memory seem to be separate issues here for the Turing machine and for you, because just that example is supposed to show you, you can massively increase your productivity just by increasing memory capacity. Whereas one of the interesting things about these neural networks is that there's no distinction between memory and processing. Processing is memory, memory is processing. They are deeply, intimately intertwined. So productivity is hard to, it's unclear how our seemingly unconstrained except by memory productivity works if we're neural networks. Whereas it's easy to explain if we're computers in the GoFi sense. Okay. Yeah.
Can processing kind of be thought as the forward propagation from the input to output?
That's right. Processing is precisely forward propagation from the input layers to the output layers. But memory is also the ways in which information propagates from input to output. So the memory in a neural network, memory and processing are not separable. Whereas in the Turing machine, it's literally physically separate objects. The tape is the memory, the read-write head has the thing, the processor in it.
Like the algorithm that adds up plus one.
Yeah.
They're not kind of different from the memory.
So the algorithm, no, the learning,
The summer.
the summer?
Like the thing that sums up the rates with
In a neural network, that's the whole thing. In the perceptron, that was, again, perceptron is just like this, but like no hidden layers. So there's no clear separation. Okay. All right. So one move that connectionists sometimes make in this context is to deny productivity. So we have problems with some sentences. I'm assured, and I cannot for the life of me parse this as a real sentence, I'm assured that this is a perfectly grammatical sentence that makes sense. The man, the boy, the girl hit, kissed, moved. And I would be grateful if anybody can tell me what that means. I swear that I'm assured by very smart people that that's a sentence. So the girl hit the boy. I don't know. I can't parse it. Yep.
I think if you wanted to sort of unwrap it, it's the man that the boy kissed moved. Also, the girl hit that boy.
Okay. I believe you.
That's the best I got.
Yeah. Yeah, it does. So this is a perfectly grammatical sentence. The problem is that it's got too many clauses inside clauses for the human brain to for my human brain to sort it out. And the connectionists pick up on things like this and say, actually, you are constrained by memory. Yeah.
I don't fully remember what you said.
Yeah. Take a shot.
Which makes sense because I'm pretty sure it's that the boy hit the girl.
Boy hit the girl.
Right? And the man kissed the boy.
Okay.
And the man moved.
Okay.
So the man moved. The girl who was kissed by the boy, the girl who was hit by the boy, who was kissed by the man moved.
Again, I'm happy to believe you. I cannot myself parse this. So you could be absolutely right. You could be wrong. I have no idea.
What they're doing is they're just adding the verb to the end of another verb that's
Right.
constrained to another subject, which is attached to the object.
No, sorry.
These three brackets.
I saw your hand first. Yeah. Yeah.
I think the way that I took it was that the boy and the girl hit the man. So the man.
The boy and the girl hit them.
The man, the boy, the girl hit. So they both hit the man. They kissed and then they moved.
Maybe. Yeah.
No, I think it's the man in the beginning is on the
So-
inside is
Okay.
description.
Yeah.
So,
So the man moved.
yeah, and then the inside is describing other details about it.
So we're specifying the man by this sentence.
Yes.
The boy, the girl hit.
And then the girl hit is also specifying that the boy.
The boy that the girl hit. The girl hit the boy, and the boy kissed the man. I mean, commas would help a lot. Okay. Let's not get too. We are straining our memory and processing capacities. So all right. So productivity is supposed to be this. Oh, we can just keep producing sentences and sentences. And the connectionists, one reasonable response is for them to just say, no, you can't. No, you can't. It's not just infinite. We're actually heavily constrained by processing. It's not just memory limits, it's processing limits as well. So that's one thing that they can say back to this argument. Okay, but productivity. We agree that we're productive in the sense that we can keep producing and producing and producing. All right, systematicity. So Google image search, man, it really comes through. If you put man bites dog, they'll be there for you. Okay, so systematicity. Here's this interesting fact about your mind. And I can say this without having interrogated you at any length, because people are just like this. If you understand the dog bit the man, you're going to be able to understand the man bit the dog. Right? And that's just a fact about us. Why? Why is that true? Why is it the case that if you understand one, you're going to understand the other? GoFi people have a good answer. Because those are two different ways of logically manipulating the same tokens. Those are just the same structure and just moving parts of it around. Connectionists do not have a good story about this. It's not to say that they couldn't possibly come up with one. That's not the argument. The argument is the answer to this question tumbles out of the basic assumptions of GoFi. It just falls out of the story automatically. And the fact is that every person that you test has this property. It's an extremely regular, it's a universal feature. People who can use language have systematicity. It's not just some of the time, we all have this. Why? GoFi has an excellent answer. Connectionists, no clear answer. Unclear. Okay. Compositionality. Another one that's really challenging to answer. So words very often, not always, but often contribute to the meaning of the sentences in a context-insensitive way. So if I say the bucket is full of water, the word bucket is doing the same job as in the sentence, the bucket is on the fridge. Same basic job, right? Same bucket. Of course, that's not always true. So if I say the man kicked the bucket, I'm saying that the man died. So in idioms, words do unique, weird things. But very, very often, words act compositionally. Now, that's to say that they contribute to the meaning of a sentence in a context-insensitive way. Regardless of the context, they contribute the same meaning. Now, in GoFi, again, that's super easy to explain because the logical properties of a symbol are the same regardless of what sentence it's embedded in. In connectionist networks, that's super hard to explain because in a connectionist network, context is everything. Connectionist networks are really, really good at dealing with context-sensitive information processing. That's one of the most impressive things about them. They're able to deal with context sensitivity. So that's why they're able to do speech recognition. That's why they're able to do handwriting recognition. That's why they're able to deal with the cat, right? That multiple simultaneous constraint satisfaction. They are excellent at context, but they're really bad at context-insensitive stuff And meaning, the meaning of words, is one of those things that is quite often, not always, but quite often, context insensitive. So the fact that we are capable of being context insensitive, rule-based, is really hard to explain if you think that the mind is fundamentally a connectionist network. Yeah? Okay. And last but not least, inferential coherence. So this is kind of just the whole, everything that I just said to you was all about understanding meaning. Now just transpose understanding meaning, all three of those properties, onto making inferences, right? So the fact is that we're able to be productive, compositional, and systematic when we're doing inferences, going beyond what we know to what is implied by what we know. So this is a logical derivation. It gives me the screaming heebie-jeebies because I'm bad at logic. But seeing a derivation now just reminds me of all the times that I screwed up derivations in front of like 300 kids. It's really upsetting. This will be with me for the rest of my life. Okay, so, but notice that everything that we just said about understanding the meaning of a sentence also applies to doing inferences, that we're capable of doing inferences in a productive, systematic, compositional way. That's inferential coherence. So, what's the lesson? They want you to think that in order to explain these things, in order to explain those four features that we seem to all have, we must be at the level of cognition where the representations happen. We must be running something like a computer. A computer in the sense that we've been talking about, a good old-fashioned AI computer. What do you think? Did that show that we are through and through GoFi machines? Here's one thing that you might think about this. Here's one conclusion. So these are groups of people competing for grant money. And if you've got two quite different groups of people competing for the same grants, it's in your interest to say that that other guy is completely wrong and my thing is completely right. But what's a possibility that doesn't involve that? They're both kind of right. They both have part of the story. So one way to, if you found those arguments convincing, but nonetheless see the appeal of connectionist networks, one thing that you can say is, look, maybe we're both. Maybe we are sometimes running a computer. Maybe we are sometimes running logical symbol manipulations, and maybe sometimes we're running connectionist networks. And part of how these people made it seem like their thing was completely right and the other thing was completely wrong is by having a kind of narrow definitions of cognition. So the good old-fashioned AI people said, cognition, that's when you're sitting down and there's a pencil in your hand and you're doing logical manipulations of things. You're doing math, you're playing chess. And the connectionists are like, cognition, that's when you're climbing a flight of stairs or like singing a song or recognizing a voice. That's what cognition is. And probably cognition is both of those things. And so our capacity to do both of those things suggests, at least to me, that probably we've got some of both of those things going on. Yeah?
Is there not like kind of a third option where, like, there seems to be a paradox going on where you can have a formal system that can represent a connectionist system, a simulated neural network, and you have a neural network which can seemingly do things like a formal system during machine learning.
Sure.
Is there kind of a third option where you don't need either, and there could be something underlying both of those that give rise to?
Sure.
Like a more food language, I guess, that it's sustainable.
Absolutely, that's possible. Absolutely, that's possible. Yeah. So we've got some third thing that can do both of those things. Perhaps, and here's the suggestion that I'm going to make, a dynamical system can do both of those things. So, but just quickly before think about how weird a proposal this is. What this suggests is that your brain is not one kind of machine. It's more like a swarm of machines or an ecology. of different types of machines. And that some of the machines that you're built out of are logical, rule manipulating, go-fi style things. Some of the machines that you're made of are skill-based, they are procedural, they deal with fuzzy, incomplete data sets well, that kind of thing. I think that that's a plausible picture. It's a little disturbing then, though, because which of those machines is you? All of them. Yes, you are the composite, perhaps, of a whole bunch of different kinds of machine, all operating in concert, sometimes operating probably in conflict. Yeah.
Why is that like disturbing when our bodies are, we have organs in our body, like there's multiple chunks of us that allow us to sustain our body. Why should intelligence be?
Because I want to be me. I'm the thing that's in charge. Yeah, yeah.
I think another reason why it is very valuable is we lose sense of control. We lose
Yeah.
self-identity.
Yeah.
And,
Yeah.
a sense of internal belonging where we feel not only responsible in an environment and a community, but also within our own, like, minds as well, to think that, oh, like, this is who I am, but to have that hindered and think that you're a composition of multiple views, that's highly disturbing.
It's disturbing to the ego that believes that that I'm in charge of me. Yeah. Yeah.
I actually kind of find it appealing because then
Yeah.
it suggests you can be whatever you want to be.
Right.
You can adapt those machines to do whatever you want it to do.
Right. Right. So there's a kind of inbuilt flexibility and dynamicism to it. And so if you've got some machine that's maladaptive, you don't have to think that's me. That's fundamentally who I am. That's maladaptive. You're like, well, that's one of my machines. Maybe you can take it in for a tune-up. Okay. Let's leave it there for today. And next time we'll talk a little bit about this idea of dynamical systems in third generation COG Sci. Thanks for hanging in.